Hello and welcome to today's lesson where we're going to look at heating and cooling curves, which forms part of the particle model of matter topic in GCSE Separate Science physics. So in today's lesson we're going to try to observe the change in the internal energy of a substance, which involves us being able to define what internal energy is, draw and label what a cooling curve shows with changes in energy store, and observe how the internal energy of a system can be changed, which falls into the following part of the AQA GCSE Separate Science physics topic, the particle model of matter. So we looked at the internal energy, the temperature changes in a system and specific heat capacity, and the changes of state in specific latent heat. So the internal energy of a substance will increase when it's heated. Heating an object puts energy into that object, or we say work is being done into the object. So when work is done into an object, the internal energy store of that object increases. Now this can cause either the temperature of the object to increase or the object to change its state of matter, but both can't take place at the same time. It is either one or it is the other. Now we can demonstrate this with a heating curve. Now a heating curve shows the change of temperature for a substance when energy is placed into that substance. So on the y-axis we place the temperature of the object, and on the x-axis we place the energy supplied into the object, or the time. And what happens is when the temperature increases, the kinetic energy store of the internal energy will change, and this is shown as an upwards line on the graph. Now when the state changes, the potential energy store of the internal energy will change. However, the important thing to note is the kinetic energy store would be unchanged. So this means the temperature of the system, which is determined by the kinetic energy store, would be unchanged. Now what this can also mean is that when we show this on a heating curve, that when the object changes state, it is shown by a flat line, because the energy is going to change the potential energy store, not the kinetic energy store. So it's hidden, this energy, from the temperature observation. And another word for hidden is latent. So the energy needed to change state is called the latent heat. It is called the latent heat because it is the hidden heat, as the energy is hidden from observation on your thermometer. Now the specific latent heat is the energy needed to change the state per kilogram of the substance, because in physics, specific means per kilogram. Now, the latent heat needed to melt a substance is smaller than the latent heat needed to boil a substance. You can tell this from a heating curve graph because the line is longer for boiling compared to melting. So this tells us more energy is needed to be placed into the substance to actually cause this boiling effect as compared to the melting effect. Now, this happens because there's a greater change in forces of attraction going from a liquid to a gas compared from a solid to a liquid. Now, we can identify the state change from a heating curve because it is a flat line. Because remember, when there's a change of state, there is no change in temperature. The work being done is being done on the potential energy store. So when there's a change of temperature, there is no change of state. And when there's a change of state, there is no change in temperature. So you can observe this on a heating curve because the flat lines show a change of state or a change in potential energy store, whilst the upwards or downwards lines would show a change of temperature or a change in the kinetic energy store. So as you can see from the particular graphic here, you can either change state or you can change temperature. You can either change the potential energy store or you can change the kinetic energy store. So when a solid is heated, work is done to the particles to make them vibrate more, which means that the temperature increases. The potential energy store of the solid remains constant, but the kinetic energy store increases. So at melting point, the particles don't vibrate any faster, meaning that the kinetic energy and the temperature are constant, but the forces of attraction that keep the particles in their rigid solid structure are broken and the potential energy store increases. At boiling point, what do we know? Well, in the liquid form, the particles are still in contact with each other but can slide past each other. As more work is done, the particles vibrate more, so the kinetic energy store increases but the potential energy store remains constant. At boiling point, the particles do not vibrate any faster, meaning that the kinetic energy store and the temperature are constant, but the forces of attraction holding the particles together are broken, which takes more energy than when melting, since all of the forces are broken as opposed to just being weakened. Now, the physics of heating and cooling cooling are identical, but just remember, heating requires work to be done into the internal energy store, but cooling requires work to be taken out of the internal energy store. So if we look at a cooling curve, what happens is the internal energy is decreasing with time as energy is being taken out of the internal energy store, not being added like in heating. So just to clarify, on a temperature curve, when the line is flat, the potential energy store is changing, but the temperature is constant because there is a step change of state. On a temperature curve, when the line is either up or down, the kinetic energy store is changing, the temperature is changing, it is not changing state. So to summarize what we've learned in today's lesson, energy is stored inside a system by the particles that make up that system. We refer to this as the internal energy store of the system. Internal energy can be calculated as it's the combined total energy of the kinetic energy store and the potential energy store of all the particles that make up the system. Heating changes the energy store within the system by increasing the energy of the particles that make up the system, which can either cause the temperature of the system to rise or to produce a change of state. If the temperature of the system increases, well then the increase in temperature depends on the mass of the substance heated, the type of material, and the energy we input to the system. If a change of state happens, the energy needed for a substance to change state is called latent heat, and when a change of state occurs, the energy supplied changes the energy stored, which is the internal energy but not the temperature. So, if we've been successful and we've learned in today's lesson, we can define what internal energy is, draw and label what a cooling curve shows with changes in energy stores, and observe how the internal energy of a system can be changed. I hope you've enjoyed today's lesson looking at heating and cooling curves, which was part of the particle model of matter topic in GCSE Separate Science Physics. Thank you very much and have a lovely day.